Congratulations, guys. You have made it to the last Slice of Physics video of this course. In this one, we're going to talk about a different kind of simple harmonic motion. We will tackle an oscillating pendulum. We have already talked about a mass oscillating on a spring, and now we're going to look at how a mass oscillates on a string like a pendulum. So we will look at how we study that. We will understand what the restoring force in this case is and draw a parallel for that force with the spring. And we will think about or derive what factors determine the frequency or the period of an oscillating pendulum. For the spring, we saw that it depended on the spring constant and the mass that was oscillating, but it did not depend on the amplitude. And we're going to see what parameters it depends on for a pendulum. All right, so let's start with drawing something that you guys are all comfortable with. By now, you have done a lot of it in this course. So let's take a pendulum. And in this point, when it's hanging straight down, it's in equilibrium. It's not going to go anywhere. Well, I'm going to, just like we did in the spring, I'm going to take the mass and pull it to one side. So let's say I pull it over here with an angle theta. That will create an arc length. So the mass was originally here, and when I pulled it there, it went a little arc of a circle. That's called an arc length. And let's call the length of this string capital L. Okay, so that's L, this is S. So we're going to draw a free body diagram of this mass. What are the forces acting on it, and what is the net force if there is one? So I'll represent the mass. By the way, this mass is mass M, so let me represent that. So I've got a mass M, and when I do my identification of forces, I do a little circle around it and realize that the only thing touching it is the string, and strings can only pull, so there will be a tension acting in this direction along the string. And that's the only contact force, and the only non-contact force is going to be weight, which always acts straight down. So there's my free body diagram. My next step in analyzing free body diagrams was to choose an axis. In this case, I'm going to choose my axis along the string, the reason for which will become clear as we work through this. And this angle here is going to be theta, the same angle that was over here. And this was my weight W. And so once I've got my axis, I've got my y-axis, I've got my x-axis that's always perpendicular to the y-axis. So this is my x-axis. And I can see that there is going to be no acceleration along the y-axis. So this is kind of like the ramp problem. We chose the y-axis in a direction where there is no action, nothing happening. So the net force along y-axis has to be 0 because there is no motion along the y-axis. So we know that the condition I need is sum of Fy is 0 because the string is not, as this is oscillating, the string is not getting stretched, it's not getting compressed, so there's no net force along the y-axis, there is no motion along the y-axis. So that tells me that when I break my weight, which is the non-behaving force in this case because it's along neither axis, I can break it into its components. So this will be Wx, this will be Wy. So it tells me that plus T minus Wy has to be 0. And so the net force in this case is simply going to be this Wx. Since Wy and T cancel each other, the only force that's remaining is Wx. So my net force, F net, is minus Wx because it's in the negative direction along the x-axis. So this is going to be minus W times sine of theta. Wy was cosine of theta since Wy is the adjacent to the angle theta, and Wx is opposite to the angle theta, so that's going to be my net force. And I can write that as minus m times g times sine of theta. All right, Now when we are working with small angles and with the pendulum oscillating, we assume that the length of the string is going to be pretty long compared to the displacement I give it when it bobs back and forth. So this S is going to be pretty small compared to the L. And so because of that, the angle theta is going to be a small angle. And you may have seen this in some other courses before. If you have not, some of this requires calculus to fully explain. But when we are measuring theta in radians, a small angle theta equals the sine of its value. So the sine of theta for a small angle equals or approximately equals theta itself, as long as you measure theta in radians. Okay, so that's important here, like it was in the spring's case as well. All our equations worked when that angle was in radians. And further, an angle theta for a small displacement is equal to the arc length divided by the radius. So theta is S over L. That's the definition of theta, which, by the way, is how we got that 2 pi as the full circle, because when you divide the circumference of a circle, 2 pi r over r, you end up with 2 pi. We've discussed this before. So let's go ahead and see what that net force ends up being as a result of all this extra things we have discussed. So my net force is going to be minus mg. Instead of sine of theta, I can just write theta. And instead of theta, I can write S over L. All right. So now S is the displacement. For small displacement from the equilibrium position, even though S is a curve, it's going to be pretty close to a straight line. So let's think of it as a straight line. And so the displacement is simply that way. And we see that the net force is, and let me just rearrange this to be more consistent with the other form we have discussed. I'm just going to move the L over here. It doesn't hurt the algebra to do that. So I've got this force now is a linear relationship to S, power of the displacement. S is the displacement. Is just 1. It's not squared or cubed or anything. It's linear. And then the negative sign tells us that it's opposite. F is opposite S, which means it's a restoring force. It's always going to be, once you displace it in a certain direction, the force is going to bring it back to where it started from. So that's why it's called a restoring force, similar to what the spring had. All right, so we see that it's a linear relationship. We see that it's a restoring force, and those two conditions end up in, as we have discussed in the case of a spring, these two conditions end up in an oscillation where it goes back and forth, and it's a sinusoidal oscillation, so it's a simple harmonic motion. So this pendulum will simply go back and forth like this, just like this mass on the spring oscillated about its equilibrium position. So now we've seen kind of the basics of the physics of how this works. We can now take a look at the analogy of what this looks like for the spring. So in the case of the spring, I had my net force was minus k times x, where x was the displacement. In this case, S is the displacement, and this mg over L looks like the k. So if we were drawing an analogy of this to the spring situation, this factor looks like the k, the spring constant for the pendulum. Okay, the reason I'm doing that is, given that we've done all the algebra for a spring, we can just use that now and talk about energy considerations and talk about the relationship of period and frequency to the other factors. So you will remember that in the case of a spring, the period t was equal to 2 pi square root of m over k. And by analogy, I'm going to use, in this case, instead of k, I'm going to use mg over L. So for a pendulum, since we've already done all the math for deriving this equation for the spring, and since we see that K looks like mg over L, instead of redoing all that algebra, I can simply just do this, where I can do the period as that divided by K, which is mg over L. And simplifying this, you get 2 pi square root of m over mg, and denominator of the denominator ends in the numerator, so I got to bring that L all the way up. The m's cancel, and so I get the expression that T is 2 pi L over g square root. So the period of pendulum oscillation depends on the length of the string, and it depends on the acceleration due to gravity. Notably, it does not depend on the amplitude again, just like it didn't for the spring also, but in this case it doesn't even depend on the mass. It only depends on the length of the string and the acceleration due to gravity. And lastly, I can set frequency, which is 1 over t, will simply be 1 over 2 pi square root of g over L. So if I want to talk about frequency of an oscillating pendulum, once again, it only depends on the length of the string and the acceleration due to gravity. So acceleration due to gravity is 9.8 as long as you're on the surface of the Earth. So it only depends on the length of the string. It does not even depend on the mass that is oscillating back and forth. So in studying the simple harmonic motion of an oscillating pendulum, we've seen that the restoring force has a linear relationship to the displacement. It's opposite in the direction, which is why it's called the restoring force. And we saw that the period or frequency, both of these are interchangeable because one is the reciprocal of the other, depends on the acceleration due to gravity g, depends on the length of the string L, and it does not depend on the amplitude or the mass. In the spring's case, it didn't depend on the amplitude, but it did depend on the mass. But in the case of a pendulum, it doesn't even depend on the mass that's oscillating. Thank you for watching this, and we will be doing some more examples in class to drive this home.